The Royal Observatory Greenwich was founded in 1675. It was an important project for Great Britain. It was hoped that better observations of the heavens would lead to better maritime navigation, and that better navigation would lead to more efficient trade, and ultimately, wealth. Such an important enterprise required an exceptional leader, and so the role of the Astronomer Royal was created to oversee the project, and they did that from here, these magnificent living quarters at the observatory. Today, the title of Astronomer Royal is an honorary one, but it's still only awarded to extraordinary people who have made major contributions to astronomy. The current Astronomer Royal, Lord Martin Rees, celebrates his 80th birthday this year, and this special programme marks that milestone. In an extended interview to The Sky at Night, he talks about the remarkable discoveries made by himself and others that have totally transformed our understanding of the night sky over the course of his remarkable career. Lord Rees has had many key academic and scientific posts. He was the Master of Trinity College, Cambridge, and President of the Royal Astronomical Society. He also held the highest scientific office in Britain, President of the Royal Society, and he is the current Astronomer Royal. In this programme, he'll tell us how he's witnessed and been involved in some of astronomy's greatest moments, from arguments about the Big Bang.
In Cambridge, there were these two dominant figures, Fred Hoyle and Martin Ryle, and I knew them both. Martin Ryle was rather upset at any controversy, whereas Fred Hoyle relished controversy.
To showing how dark matter gave our universe shape.
One of the great achievements was showing by computer calculations that we end up with a universe with galaxies in it, like the ones we see, clustered in roughly the way we observe.
And how black holes went from theoretical curiosities to tangible active elements in the story of our universe.
There was an object weighing about 10 times as much as the sun, which was emitting strong X-rays. And that made people think more seriously about black holes, and then to raise the more exciting possibility still that monster black holes might be lurking in the centres of galaxies.
Today, Lord Rees is also one of the world's leading thinkers on the future, from the nature of threats to our existence.
When we think about people who could, even as loners, cause a catastrophe, I think this leads to a tension between three things we want to preserve: liberty, security, and privacy. And I think one of them, probably privacy, is going to have to go.
To how our descendants might not be anything like us at all.
It could be that within a few more centuries, we'll be usurped by posthumans and maybe electronic, rather than flesh and blood. They may also be near immortal, and they will go on for billions of years.
Yeah.
It's all a far cry from his idyllic post-war childhood in rural Shropshire.
So for many people, an interest in astronomy comes from being a kid looking up at the stars. Was that your experience?
Not particularly. I mean, I was interested in numbers and big numbers, things, and heights and sizes of things. But I wasn't particularly interested in astronomy. In fact, I can quote two things that fascinated me when I was young. One was going on holidays in North Wales with the tides. I knew that the moon caused the tides, but what I didn't understand was when I looked at the tide tables, that high tide was at different times in different places, and around Anglesey, that's especially complicated. We have all this. So I was interested in phenomena, but not in astronomy particularly. But then I went to a school where you have to specialise at age 16, as you know, and I specialised in science and maths, partly because I was bad at languages, and I've been lazy about them ever since, I'm afraid. I went to university and did mathematics, which I rather regretted, because in retrospect, I'd done far better if I'd done a wide range of science at that stage, because I soon realised that some of my contemporaries who were doing mathematics had a different kind of mindset from mine. I had this more synthetic style of thinking, which I liked.
Attached to practical problems,
Yes,
sort of thing.
and phenomena, and trying to sort of see how things work based on simple principles, etc. And so my piece of luck, really, was being able to be a research student in Cambridge at a time when astronomy was starting to be on a roll, as it were, through discoveries of nature's black holes and Big Bang and all that.
What was the state of play when you started as a graduate student? What did we know and what didn't we know?
Well, as you imply, I've been lucky in that the 50 years when I've been following the subject has been an exciting period of change due to new ideas, much more powerful instruments in space and on the ground. But if we look back to the 1960s, that's the time when we first got convincing evidence that the universe started with a Big Bang, and also the first evidence that there are some things out there in space which have extreme physics where we need Einstein's theory of relativity, where Newton's theory isn't a good approximation.
Today, it's broadly accepted our universe began with a Big Bang, starting in a hot, dense state that then expanded. But when Martin was a student, a rival idea, the steady state theory, held that the universe did not start at all, but was eternal, everlasting.
When you first arrived as a graduate student in Cambridge, were people still arguing about Big Bang versus something like a steady state universe?
Well, that's right. Of course, we knew the universe was expanding ever since the 1930s, and we knew that our galaxy was just one of many galaxies in the universe. But it wasn't clear what the early history of the universe was like. And there were two rival theories. There was the so-called Big Bang theory. Fred Hoyle invented that name later, but that goes back to Georges Lemaitre in the 20s and 30s. This was the idea that everything started in some hot, dense state, and then it exploded away from that and cooled down. The other idea, which was developed by Fred Hoyle and Bondi and Gould in 1948, was the idea that the universe itself exists forever, and as the galaxies expanded, new ones formed in the gaps, as it were, so the large-scale cosmic scene never changed.
Did I read there was this nice idea, they came up with this idea after watching a film where the ending was the same as the beginning?
That's right. They were all based in Cambridge at this time, and they looked at this film, and I think one of them said, well, what if the universe was like that? And that led them to have this idea, and Hoyle developed it in a more mathematical sense.
The argument between Big Bang versus steady state could have rumbled on for years. But as Martin started his postgraduate studies, radio astronomy, the ability to study the universe using wavelengths beyond visible light, became a game changer. And like many technological advances, it had its roots in military conflict.
This subject started up because several of the people who had worked on radar during the war, including in particular Bernard Lovell and Martin Ryle in the UK, they came back to university work and they tried to use their expertise for astronomy. And they discovered that if you built a suitable detector, you were able to observe that there were many objects in the sky, some of which were fairly inconspicuous in visible light, which were emitting strong radio signals. And so we've got a much richer and less incomplete view of the cosmos because of these wave bands. But radio astronomy proved especially fruitful, especially because there was a class of galaxies which seemed to have some engine in their center which generated gas that gives radio emission. And some fraction of galaxies, which are called radio galaxies, are very intense. And Martin Ryle, who was the head of the Cambridge group doing radio astronomy, he realised that some of these radio-emitting galaxies could be detected by him, even if they were so far away that optical astronomers couldn't detect them at all with their telescopes.
With optical telescopes, one is limited to a range of observation about here. With radio telescopes, one can, however, detect galaxies at greater distances. And with our new large radio telescope at Cambridge, we think we are being able to detect galaxies right up to this region here.
Ryle made the point that if you had this population of galaxies which were exploding, then if the universe was evolving, the relative numbers of apparently bright and apparently faint ones would change. There'd be more in the past, more a long way away, therefore more faint ones.
If the universe was in a steady state, it would look the same in every direction, over all distances. But Ryle saw the opposite. Even so, the steady-state enthusiasts weren't convinced.
Ryle claimed, and showed in the third Cambridge survey, that the number of faint sources was too large to be consistent with a steady state. It was, as it turned out, a correct inference, but it didn't really strike much resonance, especially with Hoyle and Bondi and Gold. They were sceptical, and I came later to understand that they weren't being unreasonable in being sceptical, because although in the early 60s Ryle had this very good survey called the Third Cambridge Survey, which was reliable, he'd had early surveys which were wrong, and so Ryle's early claims were based on data that obviously wasn't reliable, and people therefore were sceptical about his later claims. Radio astronomers came from engineering and physics, the optical astronomers from different trainings in general, so there wasn't very much contact. And in Cambridge, there were these two dominant figures, Fred Hoyle and Martin Ryle, and the newspaper sort of presented this as a standoff between these two figures, and I knew them both, and they were very different personalities. Martin Ryle was rather more serious, and he was rather upset at any controversy, whereas Fred Hoyle relished controversy. And, of course, this is understandable, because if you are an experimenter, and Martin Ryle was a very hands-on experimenter who actually built his equipment, you've invested years of effort. So if someone rubbishes your results, you're deeply affected. Whereas if you're a theorist with a fertile mind, then if someone rubbishes your theories, you come up with new ones the next day. And so this debate between Hoyle and Ryle clearly took a greater emotional toll on Ryle, although he was proved correct.
As this debate continued, Martin Rees began his PhD, investigating radio sources called quasars, work that would eventually contribute to killing off the steady-state idea for good, to the dismay of his supervisor.
I was very lucky to be taken on in Cambridge and to be supervised by Dennis Sharma, who described himself as the most fervent advocate of steady-state theory apart from its three inventors. So he took it very seriously, and he tried very hard to defend it. And he had various arguments to defend it, but I think I helped to talk him out of it, because we found that if you took account of the fact that by the mid-60s, we knew that some of these radio sources were what's called quasars. So they were bright, invisible light. There was a centre of the galaxy, which we now know involves a massive black hole, which was outshining all the stars in the galaxy. So this was allowing us to get optical distances and redshifts.
If the theory of the steady-state universe was true, then the universe should look the same everywhere and on every timescale. But this wasn't true for Martin's quasars. He knew that the further back you looked, the more you found. This meant, for the Big Bang, the idea of the evolving universe became much more credible.
It was clear, even for a fairly small sample, that they weren't all the same at all epochs, and this was, I think, stronger evidence. But the most important evidence for the Big Bang was serendipitous and quite different. And this was a discovery in 1964 by Penzias and Wilson, two radio engineers at the Bell Telephone Labs, of excess radiation in their antenna, which they couldn't explain.
Penzias and Robert Wilson were trying to eliminate mysterious electrical interference in an experimental microwave receiver. Wherever they pointed the receiver, they found it, like the noise of an untuned analog television. They tried everything. They even thought it might be something to do with pigeon droppings. But the interference wouldn't go away. What they had happened upon was the faint remains of the Big Bang. What quickly became known as cosmic microwave background radiation.
The story is quite interesting because they didn't know what they discovered. They were trying to reduce the background radiation in an antenna designed by them and their colleagues at Bell Telephone Labs. And so it was a nuisance, this extra radiation. But then people at Princeton University nearby who'd been actually looking for this, they realised and told Penzias Wilson that this was actually an important discovery. And it's interesting for popular science because Wilson later said that he didn't realise how important the discovery was until he read an article in the New York Times written by Walter Sullivan, who was the leading science writer then, who used the phrase the afterglow of creation, because he'd been dealing with the nitty-gritty.
Right. He was an excellent radio engineer.
Indeed, and getting the pigeon droppings out of the machine to check that it was working properly and all that. And so he didn't think of the big picture at all. Yeah. And I think it's a lesson there in science that in many cases it's important to engage with the general public because they don't care about the details.
Right.
They're a matter for professionals, but they do care about the big picture. And there's a risk of being blinkered if you work in detail on a special topic, that you get the big picture and that the work you're doing is only worthwhile insofar as it helps to clarify a big picture.
Often, science reveals the big picture by gathering small bits of evidence, piecing them together to find new truths. But sometimes there's a giant leap forward, a sudden change of perspective. The idea of black holes had been around since the 18th century, described back then as dark stars. But it wasn't until the 1960s that anyone started taking them seriously. This was thanks to a new mathematical technique used by people working on Einstein's theory of relativity. Again, the young Martin Rees had a ringside seat.
Einstein's theory of relativity, which of course was developed in 1915, had become rather sterile backwater in physics, simply because there were no phenomena known where it was important. There was a tiny effect on Mercury's orbit, famously, but it only affected galaxies and ordinary stars in a very minor way.
And this is because relativity is important where gravity is very important.
Where gravity is very important, or where the speeds are close to the speed of light.
Right.
Yes. And that's not the case for things in the solar system or in ordinary stars. But nonetheless, in the 1960s, there was a lot of theoretical progress. This was led by Roger Penrose, then in London and later in Oxford, who used new mathematical techniques, which led to a lot of work by younger colleagues like Ellis and Hawking and others to actually work out the properties of black holes.
When Penrose is thinking about these ideas and so on, and there's this famous set of lectures that I know Stephen Hawking was packed off to go and do. I think you went to some of them as well. Did he think that black holes existed in the universe, or was this a sort of mathematical interest? Like, if that makes any sense.
Well, he came from a mathematical background, but he was steered towards this by Dennis Sharma, who was a heroic figure in this whole enterprise, because exemplifying that a great coach need not be a great player. I mean,
right. He was your supervisor as well, yeah.
He had a whole stable of students in Cambridge and then in Oxford, and he persuaded Penrose to go into this subject, and then he got students, including Ellis, Hawking and Carter, who worked out what happened in black holes. But the main distinctive thing that Penrose did, and that's because he was a better mathematician than the others, was to show that even if something collapsed in a not very symmetric way, it would still end up with an infinity at its centre, as it were. Obviously, if something exactly spherical and it collapses, you're not surprised it goes down to a point. But he showed that even if it was fairly irregular, as any real object would be, you would still have the same phenomena right in its centre. And this made people realise that black holes may exist as the end point of the evolution of massive stars. And in 1970 or thereabouts, X-ray astronomers did find that there were binary star systems where there was one ordinary star, and orbiting around it there was an object weighing about 10 times as much as the sun, which was emitting strong X-rays. And the interpretation was that it was much too big to be a white dwarf, and that it was a black hole, and gas captured from its companion was swirling into it and getting very hot. And that was an instance of a phenomenon that couldn't be explained without Einstein's theory of relativity and black holes. And that made people think more seriously about black holes, and then to raise the more exciting possibility still that monster black holes might be relevant to quasars, and they'd be lurking in the centres of galaxies.
And so we can explain these radio galaxies and these quasars, of which we see lots with supermassive black holes. There's then the problem of how you form supermassive black holes. So that was one of the objections. How do you form something that large? That was a big problem.
That's right. And of course, as we discovered more of them and became convinced of the theory that quasar phenomena involved a black hole, then people thought hard about this, and we still don't know the details. But it does seem that when a galaxy forms, some of the gas doesn't turn into stars, but remains fairly coherent and goes down into some object too big to form a star, which becomes a seed for a black hole that then goes on growing. So there is now a lot of data that the mass of the black hole in the centre of a galaxy is correlated with the galaxy's properties. And that's because, obviously, the bigger the galaxy is, the more likely it is to get a big black hole.
So that relationship's locked in at the beginning. It's something that happens
it is,
very
yes,
early
and
on.
it works both ways, because it's also thought that when the black hole gets too big, then it becomes potentially so bright and so powerful that it blows out the remaining gas. So this can explain why black holes grow, but when they get sufficiently big, they exert a negative feedback on further growth by blowing out the gas which would otherwise fall in towards the centre. So there's now quite a good story about how the black hole evolution is linked to the galaxy evolution.
Recently, it's been possible to image black holes. The first one from the M87 galaxy in 2017, followed by the black hole at the centre of our own galaxy in 2022. Black holes may once have been nothing more than a hazy theoretical notion, but they're now a core part of astrophysics and cosmology. Evidence for the remarkable progress made since the 1960s.
And so you helped work out some of those ideas. What was it that made you want to work on that? I'm sort of interested in how you've picked all these different problems that you've dabbled in.
Well, I suppose I've always been interested in phenomena rather than mathematics, and trying to understand the physics. And obviously I therefore tried to see if I could contribute to a subject which was a new subject. And I think scientists can be divided into those who tend to write the first paper on the topic and those who write the definitive last paper, tying up the loose ends. And I'm in the first category, really, trying to sort of guess what's going on and try and explain it in crude outline. I should say, and this is sort of fast-forwarding, as it were, to the last 20 years, that this whole subject of understanding cosmic phenomena has been revolutionized by the ability of powerful computers to do simulations, to simulate what would happen if gas is flowing into a black hole, and all that, and do this in enough detail, enough resolution to get a result that you can believe. And so now we can go beyond the sort of simple ideas that people like me did until the year 2000, as it were, and really learn a great deal more by doing simulations. Just as meteorologists learn more about the weather by doing simulations, we can learn about what happens inside a galaxy and inside stars by doing simulations.
But before that, you need the first ideas, which are sketched on a blackboard or pen and pencil or something.
Yes, and so I can contribute to those, but some subjects have got beyond that stage.
Right.
And I feel I can just be a cheerleader, because even if I work full-time, I could never be a sort of adept solo performer in computer coding, I don't think.
Right, so an interesting example of that, I think, is people might have heard about the wonderful discoveries of LIGO and the gravitational wave experiments, where we see, even from occasional gamma ray bursts, these ripples in space-time. But a large part of those discoveries are made because we can simulate what we'd expect. And so they can look for signals that the computer predict might be
Absolutely. That's simulating the rather complicated curved space around collapsing objects.
LIGO, the Laser Interferometer Gravitational Wave Observatory, was set up to look for evidence of some of the more extreme implications of Einstein's theories. Namely, that huge physical violence, like black holes colliding, can produce so-called gravitational waves, disruptions in the fabric of space. If such a wave passes through the equipment, its synchronized lasers will become unsynchronized.
It detects tiny ripples in space, which correspond to two mirrors of 4 kilometers apart, vibrating by a tiny fraction of the diameter of an atomic nucleus. So what they're doing is measuring fractional change in length, which is like the thickness of a hair at the distance of Alpha Centauri. So this is an amazing technical achievement, and much of astronomy involves work like that. And so it's the theorists who set the groundwork, of course, and the challenge for the experimenters.
But then often interpret the results. So just to finish thinking about black holes, LIGO, of course, has picked up signals from merging black holes. Mm-hmm. What does that tell us about the black holes themselves? What might experiments like that tell us about the black holes themselves?
Yes. Mm-hmm. Well, in principle, it can tell us about whether the black holes are spinning, etc., and about their mass. And LIGO has already revealed a surprise, because everyone expected that it would detect pairs of black holes, which would be the remnants of stars. But people thought that the typical masses of those were about 10 or 20 solar masses.
These are the biggest, the leftovers from the biggest stars.
Yes, and that's consistent with what's detected by X-ray astronomers in binaries. But they discovered some of these coalescences involves stars of about 60 or 70 solar masses, black holes of that mass. And this was a big surprise. And we still don't quite know the explanation. The most likely explanation is that the first generation of stars, which formed in young galaxies, may have been on average much heavier. There are reasons to suspect that may be correct, but this is a big surprise to astronomers that has come out from LIGO.
Black holes aren't the only important things out there that can't be seen. Part of Martin's work was to shed light on one of modern cosmology's enduring conundrums: the fact that most of the matter in the universe can't be seen, by definition. Dark matter is a description of a problem rather than a definition of a substance. It was something first invoked by Swiss astronomer Fritz Zwicky, who realized that the galaxy clusters he was studying didn't have enough measurable mass to exist. There must, he thought, be more stuff we can't see. But the idea really took off in the 1970s, thanks to American astronomer Vera Rubin.
If we plot the velocity of the planets as a function of distance from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And you can see that Mercury orbits much more rapidly than Pluto.
On the face of it, we might expect a spiral galaxy to work in the same way, with stars nearer the center whizzing around faster those further out. But when Vera measured their velocities, she found they didn't behave as expected.
If we observe the velocities of stars orbiting in a galaxy, we find that their velocities remain flat all the way to the edge of our observations. That's not what was expected. By correspondence with the solar system, and in fact just from Newton's law, it was expected that the velocities of the stars would fall off.
There had to be much more mass than could be seen. So-called dark matter. It was a realistic, if speculative, explanation. Then, in the 1980s, Martin and his colleagues realized that dark matter might have played another vital role in forming the universe we see today.
What happened then was people were able to study the microwave background radiation, the relic of the early universe, and find that it wasn't completely smooth over the sky. They found that it was a bit irregular. Some patches were hotter, some patches were slightly cooler. And what this meant was that some bits were denser than average and some less dense than average.
So even the early universe was slightly lumpy?
Yes, it was. And indeed, had it not been so, then after 14 billion years, it would still be uniform neutral hydrogen with no stars and no people. So It had to be slightly irregular to allow some bits to concentrate and turn into stars and galaxies. And for this to work, the dark matter had to contribute 5 or 6 times more mass altogether than the ordinary atoms. And it had to have the properties of a swarm of particles which didn't interact with each other and didn't emit or absorb light, but didn't then and still don't know what it's made of. It's just it's made of something which seems, or at least most of it anyway, to be in the form of these non-interacting particles.
It's an interesting status of the theory at the minute, isn't it? Because we have this, as you say, this picture gives you a really good description of how galaxies form and how we end up. You have these dark matter halos with our galaxy sitting in the middle. On the other,
Collider in Geneva, and this can detect particles up to a certain mass, but there's a factor of about 1 billion between the maximum mass that it can detect and what might exist. So there's a huge range of parameters where there could be these particles which are very, very heavy, and they'd still behave the same way. Now, they could even be as big as little black holes. And one of the great achievements which came in the 1980s and onwards was showing by computer calculations that starting off with a universe like we infer from the background radiation, with the fluctuations we see there, and running things forward, we end up with a universe with galaxies in it, like the ones we see, clustered in roughly the way we observe. And some of the gas dynamics, etc., is fed in, isn't fully simulated, but this is a pretty good story, which fits amazingly well and has stood the test of time. And this really developed in the 1980s, and I followed this closely. I'd done some of the similar work relevant to it in the 70s, and in later decades, then not only the observations got much better, more precise, and they've vindicated this theory, and we've also been able to probe far back in the past and actually understand how galaxies evolved. So it's a really impressive way things have advanced.
And it's, in some sense, it's another pillar in favour of the idea of dark matter. So we know that
That's right.
We need it to explain galaxy clusters, we need it to explain individual galaxies.
Yes, yes.
We also need it to explain the large-scale structure that we see.
Well, that's right, and to explain the lumpiness of the universe at early times.
Right.
Because those observations wouldn't have fitted together with the present-day observations if we didn't have the dark matter.
As if dark matter wasn't challenging enough, another of Martin's interests is the idea that this universe is just one of many, in a multiverse sort of system, where things are perhaps even stranger. One of the questions that the Big Bang raises is what came before the Big Bang. One such answer might be that our universe is far from unique.
You have Swiss cheese, okay? And in Swiss cheese, you have these bubbles there, okay? So just imagine that the cheesy part of it is heavy vacuum, and the universe expands, and these bubbles appear inside.
It might sound fanciful, but serious scientists are giving it serious thought. And Professor Linde has even worked out how many universes there might be.
And that gave us the number 10 to the degree 10 to the degree 10 to the degree 7. This is a huge number.
But as neat as it sounds, the idea brings yet more questions, all of which deserve our attention, according to the Astronomer Royal.
If we can actually find some evidence that there were many Big Bangs, maybe we're due for a fourth Copernican revolution, where we show our Big Bang is one of many. But then, if there were many Big Bangs, this raises further speculation. Would they all be duplicates of ours? Or might they be governed by different laws? Because certainly some of the theories, like string theory, predict that there could be many, many different forms of empty space, as it were, different vacuum states,
right.
And each of them would lead to or be an arena for different kinds of microphysics. And so if you imagine a universe where the strength of gravity was different, the nuclear forces were different, etc., and it's quite fun to see what ranges of numbers would allow complexity to evolve.
So one doesn't go as far as saying, well, I need it to be about 20 degrees centigrade on a summer's day to make life tolerable. But you do need a universe that can support complexity for there to be life, which means, for example, I suppose, it needs to last a particular time. Right?
Yes.
Universes that collapse quickly don't
That's
produce,
right. It needs to last, and gravity has to exist to hold things together, but also it's got to be weak, because if it's too strong, then things the size of us would collapse under gravity. So gravity is crucial, but if it was too strong, then stars would be short-lived gravitational fusion reactors. They wouldn't provide an environment for planets and life. So gravity has to exist, but it's got to be weak. And of course, the nuclear forces have to allow a periodic table, etc. And so there are various constraints, and you can sort of map out in parameter space what the regions are which would have allowed any kind of complexity. Of course, we shouldn't be too specific about the kind of complexity that we're interested in. We shouldn't try and see what was needed for us to exist. But I think it is interesting to ask what are the constraints on the numbers if there is to be evolution of complexity of a kind which is a prerequisite for any kind of life. Because some people think that this is all metaphysics. I would say it's not metaphysics, it's speculative science.
Right.
And if we had a theory that told us about string theory and told us about whether there were many Big Bangs or not, then we would then try and see what's the probability of different sets of fundamental constants emerging. We want to do that. But I think when I give talks about this subject, I do it in a slightly apologetic way, but I say that even if you don't take seriously my motivation, then it's interesting just to consider counterfactual universes, rather as a historian might consider what would happen if the Brits had fought better in 1776 and America remained a colony and things like that. And as you know, historians do that sort of thing. And in the same spirit, one can consider these counterfactual universes. And just to take a couple of examples, we don't understand why the universe has these fluctuations which are big enough to allow structures to form not too big, and we can understand why if they were too big or too small, we wouldn't get galaxies.
You'd either get no galaxies or one big lump of a thing. Yeah.
And we can also ask what would the universe be like if there were no nuclear force. There's what I call a nuclear-free universe,
right,
where there'd be just hydrogen, no periodic table and no complex life. But incidentally, the universe then, if you kept everything else the same, would, in broad outline, look the same as it actually does.
You'd still form stars.
You form
stars,
stars, and the stars would, they wouldn't get nuclear energy, but they'd go on contracting until they became white dwarfs or neutron stars or black holes, and the sizes and stars and galaxies would be the same. So I like to say that this nuclear-free universe bears the same relation to the actual universe that a marble statue does to a real human body. In outline, it would be the same. And so one could do this for other laws, and if gravity was too strong, then, of course, you get a small-scale, speeded-up universe. So I think it's developed one's intuition to think about these, but we're a long way from having a theory which can actually explain these numbers. One day we may have a theory. Or another point that's worth making is that it could be that there is a theory, but it's just too hard for our brains to grasp, because one thing that we learn as astronomers is that there's nothing special about humans in the evolutionary tree. I mean, we know we're the outcome of 4 billion years of evolution, and many people tend to feel we're the top of the tree, we're the combination. But of course, no astronomer can believe that, because we know that the sun is less than halfway through its life, and the universe may go on far longer, even forever. And so there could be some important transition in the near future, maybe to electronic life, etc. But there's no reason to think that our brains are matched to understanding the deep aspects of reality any more than those of a monkey are.
Right, the universe doesn't owe us an explanation.
No, and there may be some deep aspects of nature which are beyond the capacity of our brains to ever absorb.
If you've been engaged in studying the mind-bending properties of the universe, then the search for extraterrestrial intelligence, SETI, may come as a bit of light relief. But what was once considered a fringe activity, Martin feels deserves serious consideration.
It is one of the interesting things looking at all of your work is how you've been willing to get involved in broader areas like discussion of multiverses, and you've been involved a bit in SETI and other things as well. How do you think SETI has changed over the time that you've been working, this search for alien life?
Well, I think the big thing, and this is a big thing not just for SETI, but for our understanding of the universe, is the discovery of exoplanets. Of course, they weren't a huge surprise in a way to many people, but it does change your perception of the night sky if you know with confidence that most of the stars you see are orbited by retinues of planets, just as the sun is orbited by the Earth and the other familiar planets. It makes the night sky much more interesting, it makes the cosmos much more interesting. And this discovery, of course, dates back to the 1990s, and the first planet to be discovered orbiting an ordinary star was co-discovered by my colleague Didier Queloz, who got a Nobel Prize for this a couple of years ago, and he's, with others, gone on to discover many hundreds of these.
We're up to over 5,000 now.
Well, indeed, they're in our local parts of the galaxy, but the expectation is, if that's a fair sample, that most stars have some planets around them, and probably, I've seen a number quoted 1 in 6, but that's pretty uncertain, 1 in 6 would have a planet like the young Earth, in the sense of being about the size of the Earth and at a distance from its parent star such that water can exist, neither boiling away nor staying frozen.
Right.
So these are all potential locations for life. And this certainly is going to motivate people to think about the likelihood of life and, of course, to look for any evidence of life on some of these exoplanets.
Since the 1960s, science has had a tool to cut through the speculation about alien life in the form of the famous Drake equation. The brainchild of American radio astronomer Frank Drake, it takes all the factors we think are needed for life to emerge and uses them to estimate the number of civilizations the Milky Way might produce. It turns out there may be 50,000. But Lord Rees has reservations. He thinks there may be many more, or at least that we may eventually find evidence for many more.
The point here is that it's taken about 4 billion years for the first life to evolve into the marvellous biosphere that we are surrounded by and we are part of. And that's led to us, and it's led to a technological civilization which has existed for a few millennia, or less, depending on what you count, and has enabled us to produce manifestly artificial phenomena that could be in principle detected by another civilization. But if we think of the future, then, as I've written in other contexts, it could be that within a few more centuries, we'll be usurped by posthumans and maybe electronic rather than flesh and blood. And that they may be on Mars, or they may not want to be on a planet at all. They may prefer zero-G. But if they are electronic and they prefer zero-G, they may also be near immortal, and they will go on for billions of years.
And likely undetectable as well. Something floating between the stars.
Well, but they could be detectable. But my point is that if we detect something that is manifestly artificial, then it's far more likely to be an electronic legacy of a civilization than something which was synchronized to within a few thousand years. Because if we imagine that another planet evolved like the Earth, then it won't have evolved at quite the same speed. It may have had a head start of 1 billion years and gone to our phase 1 billion years ago. It may be slow, etc. But to be synchronized within a few thousand years, which is the lifetime perhaps of a flesh and blood technological civilization, is very unlikely. Far more likely that it's 1 billion years behind us, in which case we won't see anything, or 1 billion years ahead of us, in which case what we would see is evidence, electronic evidence of the remote descendants of that civilization. So my line is that the Drake equation, which puts in a lifetime of civilization argument, is very pessimistic because it only takes account of the time when the flesh and blood civilization exists. And that may be short compared to the time in which these electronic entities would manifest themselves.
So we've talked about artificial intelligence and the far future, but you've worked on a huge variety of topics. You've written about risks to civilization, you've looked at the far future of humanity and our next century and whether we'll get through it. How did you get involved in these broader issues beyond cosmology, beyond astrophysics?
Well, I think I was always keen on politics. I went on CND demonstrations and things like that, and I became involved in the Pugwash conferences in the 1980s, which were concerned with arms control, etc., and was privileged to know great figures like Rotblat and Rudy Piles and things in the later years, and felt it would be sad if there were no people in the younger generation who took up their torch, as it were. So I got involved in that. But then, later on, when I became more senior, I became president of the Royal Society, and it was then part of my duty, as it were, to become engaged with science policy across the board. And so that gave me an opportunity, as well as an obligation, to take a broader interest in politics and policies. And that led to my greater involvement in these things and speaking and writing more about these topics, as well as about astronomy. I suppose this was, to some extent, related to the fact that my day job was being an astronomer, as it were, in that one thing that we are more aware of than most people is the far future. Most people are not aware that the future is at least as long as the past, and that we humans are just on the way to some new kind of species, etc. And that if we screwed up and stuffed ourselves out, then this would be catastrophic, not just because we destroy what's there now, but would destroy huge potentialities. So that perhaps gave me an extra motive, through being an astronomer, to worry more about the threats. And of course, when I say I'm an astronomer, and it's probably the same for you, people think you worry about asteroids and all that. And of course I worry a bit, but asteroids are a risk that we can quantify. We understand enough about it, and we know it's small. And we also know, more importantly, that it's not getting any bigger.
Right,
it's not
there aren't
by
new
us.
asteroids turning up.
That's right. But whereas the threats that I think we need to worry about are those which are new and growing, caused by human beings. And these are of two kinds. One is our impact on the environment and resources, climate change, biodiversity, etc. But also another kind of worry, I think, is technology getting out of control. And one thing which I first wrote about in a book 20 years ago, and I think is now even more serious, is the possibility that even a few ill-intentioned dissidents with technical expertise now have the power to cause a global disaster. I'm thinking of massive cyber attacks and bioengineered disaster. And so I think this is a big worry, and it's a big challenge to governance to ensure that we can minimize these risks. I think it's very hard because it's okay to say we regulate them, but we've not been very successful at regulating globally the tax laws or the drug laws.
Right.
And when we think about people who could, even as loners, cause a catastrophe, we've got to worry about this. And I think this leads to a tension between three things we want to preserve: liberty, security, and privacy.
Yes.
And I think one of them, probably privacy, is going to have to go.
Yes.
So I do worry about these things, but this has been something which is separate from the astronomy, in a way motivated by an awareness of the far future, and also perhaps an awareness, living in an ancient town and university, of the legacy that we owe to centuries past. I think we know when we look around us, in Oxford and Cambridge in particular, how much we owe to those who built the cathedrals and the colleges and all
right.
that. And it would be shameful if we left a depleted world for next generations. So those are the two reasons where my other life has motivated me, but I think it's really otherwise been separate.
There's one other thing, which is that there's a grand astronomical tradition of talking about things in public and to the public. I think we're good at publicising our science and talking about it, as you've done today.
Yes,
so that you've also always tried to talk in public about what you're doing, which is of course part of your role as a astronomer royal.
Yes. Yes. Well, but I mean, I think we are lucky in astronomy that the public is interested. Space and dinosaurs fascinate young kids, and many of us retain that interest later in life. And I think we are lucky because even those who are fascinated by science are slightly ambivalent about some sciences, like, say, genetics and nuclear science. Whereas I would say astronomy and probably ecology as well have an unambiguously positive public image. Because they don't have the downsides in the way that the other two I mentioned did. And so I think there's a public interest and a pleasure in hearing about these subjects.
We've talked a lot about your science, but I should ask about the role of astronomer royal. That's, of course, how lots of people know you. What exactly does the role involve?
Well, it's a bit anachronistic because, of course, as you know, it was the title of the person who ran the Greenwich Observatory, Flamsteed, 1675, and his successors. But it became an honorary post when we stopped being able to do observations from Greenwich and did them overseas. But they kept the title as an honorary one. But it implies, I suppose, a commitment to bang the drum for astronomy, etc. And I did one specific thing, actually, well, small but distinctive, which was that in 2014, there was a tercentenary of setting up the Longitude Prize, which famously was eventually won by Harrison for his chronometers. And I thought that since there had been a number of challenge prizes over the subsequent centuries, it would be nice to have a big British one again in commemoration of this. And I talked to a couple of ministers and others, and they agreed to set this up. I felt that if anyone was going to take this initiative, it should be me, because the original Longitude Board, which was like the first research council in a way, and it went on for 100 years supporting expeditions, etc. This had 8 ex officio members, and 3 of them were the Astronomer Royal, the President of the Royal Society, and the Cambridge Professor of Astronomy. And having held all 3 of those, I felt that I perhaps had a sort of obligation to ensure that the work of the Longitude Board wasn't forgotten. And that has led to what I hope will be a succession of challenge prizes.
And I guess, as you said, there's been plenty of drum banging as well for astronomy in general, but also for British astronomy. And this is a place where there is lots happening in this country.
Well, indeed, astronomy has a strong role going back to Captain Cook and the transit of Venus and all that. But I think we've had a strong tradition. In the recent decades, when I've been involved, it's been gratifying to see that the subject has become taught more in schools, and particularly in universities. There are lots of departments teaching physics, but many of them have now turned into physics and astronomy departments, because astronomy is an increasing part of physics and a way of enriching the physics curriculum with some interesting examples. And so we in this country, especially because we've been able to collaborate with our European partners in ESO and the European Space Agency, have a pretty high role, and it is a specially international subject, and that's one of the bonuses of being involved in it.
So just to finish off, looking at the future, you started by saying that you were lucky to work in this time when astronomy had new technologies and new ideas. Yes. And great people and so on. If you were advising a young scientist now, an early career scientist now who's just starting, are there areas where you see the same sort of excitement?
Well, I think what's been so positive is that the 5 years when I was young were exciting, but the most recent 5 years was all the work on exoplanets, gravitational waves, and new ideas about space exploration are just as exciting. So I would say that for people joining now, it is just as propitious a time. The one difference is that I think they need to have wider expertise now, because we need to be computer experts to a greater extent than I am, and also physics, chemistry, and maybe even biology. So it's a cross-disciplinary subject in a way it wasn't in the past. But the wonderful thing about it is that it is a subject that appeals to a wide public, and also it's international, because the night sky is the most universal feature of the human environment, and for that reason also it's a more interactive and international subject than almost any other science. And so it's got all these pluses.
All of which have added up, I think, to you having an awful lot of fun.
Well, indeed, I've been lucky. I think perhaps in some respects scientists starting now aren't quite so lucky, because the subject is rather more crowded. When I was young, the young outnumbered the old, because there'd been an expansion in universities, and therefore there was less competition, etc., and quicker promotion. And I do worry about the amount of bureaucracy and the competition of a negative kind which is imposed on those starting science today. I hope we can avoid that, because the payoff, if we allow and encourage bright people to go into science, is very high indeed still.
Well, on that note, we've talked about a remarkable range of things. I think we've covered all scales, the far future and the distant past. So I just want to say, Martin, thank you very much for talking to us, and I'm sure we'll talk again.
A remarkable man, an extraordinary career. A very happy 80th birthday from everyone here at The Sky at Night. That's it for this extended programme, but do join us next time, when we'll be transferring our attention from the night to the day. Until then, good night.
Enter a labyrinth of curiosity to find answers to questions that have mystified, perplexed, and challenged. Simply listen to Inside Science, now on Sounds.